Hello, this is section 9.7 on linear, quadratic, and exponential models. So we've had a chapter. This whole chapter has been about quadratic functions, and today we're going to focus on this learning target of choosing linear, quadratic, or exponential models for data. So we're trying to decipher between the three common ones that we've done so far this year. And you can see my picture for a um, quadratic for this one is part of, if you can tell, it's actually part of the Eiffel Tower. All right. So first of all, linear, quadratic, and exponential functions. The here is the what the equations would look like. So linear, of course, is y equals mx plus b. Quadratics are in the form y equals ax squared plus bx plus c, and then exponential are y equals a times b to the x power. And the graphs are also very important. You can tell from a graph whether it's going to be linear, quadratic, or exponential. Linear makes a line. Quadratic makes the u, or the upside down u, and then exponential just makes that little curve. So choosing by graphing. So this is a very easy way to choose the best which model it is. Um, and it's just by plotting your data set. Okay, if you're given it in ordered pairs, if you're given it in a table, go ahead and plot it and determine if it's a linear, quadratic, or exponential. So this one you graphed it, and if you connect the dots, you see it'll make a, oops, sorry. You see it'll make a U type of a graph going on forever like that. And of course, if you make the U, that's a parabola, and that is a quadratic model. Second one, that one does have a little bit of curve, but it's not making a U. As far as we can see, it's not making a U. So we're going to assume that it doesn't make a U, and it just keeps on that curve. It's definitely not linear. It's not quadratic, so it is exponential. All right, and we're not going to make the equations right now, but this last one, when you plot them, it does make what looks to be a straight line, and I believe it is. So that would be a linear model. All right. So once you try this on your own, I have one set of data points, and I want you to determine if it's a linear, if it's a quadratic, or if it's an exponential model. All right, so plot the points. You can make your own little graph on your notes if you want to grab graph paper. Otherwise, pause it, and when you got it, once you unpause it and see the correct response. All right, this model, it has a curve, but it's not a U, so it will make a exponential model. All right, why don't you try this one as well? You can pause it and you can plot these and see what this one is going to end up being. All right, so this one, when you graph it, it doesn't quite fit on this graph with the negative 211. You also have positive 211, and without it, it kind of looks like it'd be a V. However, it is going to be a parabola. It's going to have the U-shaped type thing, and that would be a quadratic function. All right. So choosing a model using differences or ratios. So we just talked about graphing. I think graphing is the easiest if you're able to graph. But differences or ratios is another way to check to see if what type of a model it is. So for linear, if you look at the x's and the y's, you would add or subtract the same number each time. So it has a constant slope, constant rate of change. So let's just say as the x's go up by 1, the y's all go up by 4. That would be constant rate of change. For it to be exponential, it have to multiply by the same number each time. So as the x's go up by 1, the y's multiply by 6 every time. And interesting for quadratics, if you find the differences, so as x's go up by 1, the y's may go up by a different amount, but then find this or subtract the differences. So, and we'll go through an example of that. The second differences, if they're the same, then it would be quadratic. So hopefully we get to an example that's like that to show this. All right, so this first example A, let's see if I can get it here. What type of function best models of data use the differences or ratios. So if you look at this, x's go up by 1 every time, y's go down by 4 every time. So that means it has a constant rate of change. It is a linear function. Now the second one, it does not have a constant rate of change, but it's also not just multiplying by the same number every time. So if you look at the second differences, because the first difference is it goes down by 0.25, then by 0.75, then by 1.25, 1.75. The difference between those differences is going to be subtracting 0.5 every time. So the second differences are the same, which means that's where we're talking about quadratics. So the second differences are the same, so it is a quadratic function. So why don't you try that now? Oops. Let's see, how many do I have here? I have a graph. You can use the graph, but I would like you to try it without a graph. Um, it says which type of function best models the ordered pairs. Those ordered pairs. Use differences or ratios. So why don't you pause it, try it, see if you can figure out which one it is, and then I'll show you the result when you unpause it. All right, so this one I like to write on like it's a T-chart so I can see it more visually. It's easier to see what the differences are. And in this case, it multiplies every time. Multiplies by 2. So if it multiplies by the same number on the y values, it will be an exponential function. Now, one review of writing equations for functions, and we're not going to do too much of it, but I want you to know and review how to do it. A couple of them will be easy to remember. But so look at number 1 there. Review. If to check to see if you get the y, or sorry, check to see if you get the y value by adding the same number each time or subtracting. If you do, then the function is linear. We determined that already. And you'll use the formula y equals mx plus b. So remember, that is is the formula for um, linear equations. The m represents the slope, and so that's the change in y over change in x, or the rise over run. And the b represents the y value when x is 0. In other words, that's the y-intercept. So that's linear. Recap for exponential. If the function is not linear, then you can check to see if you multiply by the same number each time. If you do, then the function is exponential, and you'll use the formula y equals a times b raised to the x power. The y value, the a is actually the y value when x is 0. Again, that's the y-intercept. The b is the number you multiply each time, so that would be your common ratio there. And then finally, if the function is neither linear nor exponential, then you will determine that it's quadratic in this chapter. Okay, we've talked about that. If the function is quadratic, you will never be asked to write the equation for that when it's in quadratic. So just note that. But let's take a look at a real world example and see if we can determine what it is. And this is going to be our last 2 problems here. So transportation. The data at the right gives the values of each of a used car over time. Which type of function best models the data? Write an equation to model the data. Now, it might not be perfect because cars change, depends on weather and stuff. But if you're looking at it, let's look at the differences. So we want to first see if there's any common differences. Or you can graph it. Again, graphing it helps. This looks like it's close to linear, but not quite. It looks like there is a tiny slight curve. So it has a slight curve. But it doesn't look quadratic, so maybe it's exponential. So let's look at the data. The first differences are definitely not the same every time, but the second differences, the first differences are the same, but it's a multiplication. So you go backwards, you do 11,065 divided by 12,575 to get whatever you multiply every time, and it's about 0.88 every time. There's one where it's closer to 0.87 if you round, but again, it's not going to be perfect. So if you do multiply with the same number every time, of the money through the years, it is going to be exponential. So we know it's exponential. Let's write a model. So that would be y equals a times b raised to the x power. And we'll say a is our initial value. So that should always be our starting point. and that would be 12,575. And the decay factor is 0.88, because if you multiply something by 0.88, it'll be going down. So our equation then would be y equals 12,575 times 0.88 raised to the x power. Okay. Finally, step 4, it says you can go ahead and test 2 of the points to make sure it works out. And it should work out or be very close to working out. In this case, it does work out. So, what I'd like you to do then is to try this one. It says the table shows the annual income of smaller theater company. Which type of function best models the data and write an equation unless it's a quadratic function? Okay, so if you'd like to pause this one, try it on your own, and then I will show you a result in a second. Pause. Alright, so this one dealt with theater company annual income over years. So it is going up slightly each year. And the thing is, it's not going to be perfect, but it's very close to the same. 476, 475, 480, 480. So we're going to say it's going up by 480 each time on average. And we're going to make it a linear, it's going to be a linear function then. Linear. So that'd be y equals mx plus b. In this case, the constant change would be 480 over 1. So that's going to be 480, that's our slope. Plus whatever the starting was, and you started with 18,254. So there's our linear equation to model this general data set as closely as we can. Alright, so that's writing an equation. That's determining if it's linear, exponential, quadratic, and writing an equation for it. And that was with some real world problems right there. So let's revisit. Our goal was to choose a linear, quadratic, or exponential model for data. And I think we've done that today. So there are similarities between the three, but they are all different and they're unique in their own way. And our job here today is to determine which is which.